Our first presenter today is Dr. Gotchev, who's with us in from Finland. I appreciate the journey that he took. He is a professor at Tampere, is that how you pronounce it? University of Technology. And he is working on algorithms for multisensor 3D scene capture, transform domain light field reconstruction, and Fourier analysis of 3D displays. So today he's speaking on a very interesting topic on architectures and codecs for real-time light field streaming. Thank you very much, sir.
Thank you for the introduction, and good morning, everyone. This is work performed by a team from Holographica from Hungary and Tampere University of Technology, where one of my students recently moved to Nokia Tech. It comes here as a JIST-first, so there is a journal article behind this presentation, and you can find all details in this article. We work with light field displays, and the main aim of such displays is to recreate the continuous parallax. Along with the binocular 3D visual cue, we want also to support continuous parallax, which is like seeing the objects in the scene from different positions with the correct perspective and with a naked eye. This naturally requires a wide set of light rays, and such a set is fairly easy to generate by geometry-based applications like computer graphics. However, when we come to representing and recreating real or natural 3D visual scenes, like 3D light field videos, we face up the problem of its compression, because the amount of rays we handle with the current light field display is about 100 megapixels, and it is growing for attempting higher quality. So our specific aim is real time. So we want to be able to render light field video in real time. The phenomenon we are dealing with is, of course, light field, and we usually start with the Plenoptic function, which is 7D function describing all rays in the space with their location and direction. And then we go to its 4D approximation, which is the 4D light field, which is nicely parameterized by two parallel planes. And then each ray is characterized by its indices while crossing these two parallel planes. It is very natural to associate one of the planes with the camera positions or camera plane, and then where they focus is the image plane. So we essentially sample or sense the light field by a rig of cameras. For full parallax, we have a matrix. For horizontal only parallax, we have a horizontal rig of cameras, something like this. So we put the cameras some distance away, and then we have also the distance between pixels, which allows us to parameterize the imagery through the directional and spatial location, and then to recreate such a light field by projection-based light field displays, which is maybe the most direct form of recreating the light field. So we put optical modules, essentially projectors, with certain spatial resolution, and they emit their rays, which recombines at some plane, where we put what Holographica called holographic screen, which is essentially a diffuser which keeps the direction of each ray, transforming it into a tiny beam in horizontal direction and wide beam in vertical direction to maintain the horizontal parallax. We can maintain, of course, a full parallax, but this will require square number of projectors, which is technically quite demanding. So the role of this holographic display is like a discrete to analog converter. So you can think of the rays coming from the projectors like discrete Diracs, And then the holographic screen makes the continuous discrete to continuous conversion. So at the other side of the screen, we get something like continuous light field with continuously supported parallax. We can describe the process of formation, the light field, describing how each ray propagates from the projector plane to the screen plane and then further to the camera or viewer plane. So given the field of view, given the spatial resolution of each projector, given the interval between the projectors, we can describe the topology of light rays coming from the rig of projectors. And then we can put them into ray phase space, like this is the spatial location, and this is the angular value of each ray. So at the projector plane, we have something like very densely indexed set of rays, which, when propagating toward the screen plane, change its direction. So it's like the shearing operator, which is well known in light field propagation. And then it goes further to the camera or viewer plane, where it changes further. Which means that the same ray, they appear at different locations at the camera views with respect to the rays generated or needed by the projection engines. It is possible to analyze all these effects given the parameters. Now, in this picture, the display, the projectors are here and the camera is here. For some reason, but knowing the topology of the optical engines, optical modules, and their fields of view, one can find an optimal position of the cameras, which will reproduce the same set of rays. We have done this, also proposing a methodology how to analyze the display in spectral domain. There is a journal publication in Optic Express, which I'm only referring to here. But the main point is that what we feed to the displays, to the projectors, are not discrete views. So this is the big difference between autostereoscopic displays and light field displays, where in the autostereoscopic displays we want to have discrete views with certain disparity to create the binocular effect, while here we feed the projection modules with what we call light field slice in order to maintain the directionality and the spatial location of the desired light fields, light rays. So basically what we put at each projector is something like an image, but it is a combination of rays or parts of the camera views. So this is something that it is in a more central position. Those are the projectors being the far ends of the projection rig. So essentially what happens is that it is a light field conversion between the given views and the light field slices at the projectors. And we have these correspondences where we have something which is describing the scene, the 3D visual scene, which is display independent, but then we have to recombine, perhaps to interpolate some rays in order to create the rays which are corresponding to the topology of the projector. So and this is something display specific. When we are doing this, we need computing power, which is usually supported by GPUs. So we have rendering nodes. Usually one rendering node supports several neighboring projectors. And one GPU output is usually running one light field slice. In terms of number, for example, we might have something like 72 projectors run by 6 computing nodes or 6 high-performance computers with where each of them controls something like 12 projectors. by, for example, 3 or 4 GPUs, depending how many outputs each GPU has. So in order to handle the data from such a topology, from camera to display modules, optical modules, we need to encode each camera stream and then to present the proper rays to each renderer. Now the brute force, the direct approach, is to present all light, the entire light field to each of this decoder renderer chain. So that each decoder decodes everything, all streams, and then pick up the rays needed for this particular projector position. While this is a kind of naive approach, it also allows to analyze the bottlenecks and to see how to address them. So one observation is that actually when we are having an individual view, stripes or vertical blocks go to nearby nodes, like 4, 5, 6, while more distant nodes are taking stripes which are more distant. So, for example, such a view will serve several nodes in a particular manner. So if we can ensure that the corresponding nodes or renderers have access to this part or to this part, respectively, we are somehow good. So the first architecture would be a two-layer architecture. We again encode each individual camera stream, but then we decode it individually. And then here we don't have the problem of a very wide bandwidth streaming channel, while we need to have a very high speed interconnection between the decoders and the renderer, so that the renderer can pick up what it needs to render. So what we have at the first layer, we have a processing power which is arbitrary. It is well scalable, so we can select as many nodes as we need, depending on their performance, and we have no redundancy in the decoding. Then in the interconnection and the rendering layer, we have an upper bound determined by the resolution and number of optical modules. And we have this need of high-speed interconnection, which is kind of expensive. The alternative architecture would assume one layer, so we again recombine decoder and renderer, but make sure that the decoder has random access to the encoded streams so that it can perform partial decoding of image regions. Then the decoding speed would depend on the size of the image area. To this end, we selected 4 out-of-shelf codecs, JPEG, JPEG 2000, H.264, and HEVC, in order to analyze their support of partial decoding and to compare, to measure the speed up achievable by partial decoding. We use Big Buck Bunny as a test scene, represented by 80 views, each of HD resolution. In H.264, we have functionality which is called slices, and those are different slices in terminology. Those are not the light field slices we provide to the optical modules, but those are slices formed by groups of macro blocks in the H.264 terminology. So those are parts of each frame. And then when it is an intra-frame, slices are encoded independently. So there is no spatial motion estimation and prediction across the boundaries of the slices. However, all current implementations of the motion prediction through P frames and B frames actually discard this, disable this, disregard the slice boundaries, which means that if we run it directly, we'll have some propagation of false or bogus colors in the areas which we want to decode from the areas we want to disregard. So we had to modify the encoder in order to support self-contained slices, so that also the temporal prediction is done in slice-wise manner, and we don't have motion vectors which are presented across slice boundaries. Then, having this self-contained slice, the direct way is to drop the network abstraction layer units. It is like they were dropped by the network. They were designed originally to be packed for a network transmission and then to be handled by error correcting codes if some of the NLA units are missing. So basically we disable the error connection. The stream comes to be like broken, but it is decoded faster because of not dealing with redundant NLAs. When we are doing this, we can compare the frame per second improvement, the speed in terms of frame per seconds, along the versus the part of the image to be decoded. So you can see that it is kind of improving, but not really in a linear fashion. In HEVC, we have a similar concept called tiles. They are more arbitrary, like a video frame can be partitioned in rectangular partitions, and then the tiles can be encoded separately in terms of entropy coding. Again, along the temporal dimension, this is not supported. So we had to again modify the encoder to make self-contained tiles, which decrease a bit the performance, however, makes the quality higher. Also, because of the higher complexity, the decoding runtime is lower. However, the compression is better. In JPEG, we have this partitioning in 8x8 pixels, which are processed like in discrete cosine transform domain DC and AC components separately, which they go through Huffman coding. And actually, the Huffman coding here is the bottleneck, because the decoder requires the entire Huffman code in order to decode it and then to start processing it through the inverse transform, dequantization, and whatsoever. So if we directly go with this and skip only parts which are related with inverse transform and dequantization, the improvement is only marginal. However, we can utilize another instrument in JPEG, which is called restart intervals or restart markers. So we can stop the entropy coding at n units. So we can, instead of having the whole picture in one entropy encoded stream, we can partition it in several streams. So we can put essentially the desired and undesired blocks in different stream, and then the speed up is more significant, like this, in terms of the image area to be decoded. In JPEG 2000, the partial decoding is a built-in feature, so we had to do nothing, just took one of the commercial available codecs and see how it performs. Analyzing the architectures, it's clear that the two-layer architecture is massively scalable, so we can play with the number of decoders and renderers. We get an arbitrary number of views, arbitrary resolution can be supported. However, we need this high-speed network, albeit it is in the display side, which is kind of costly. One-layer architecture, we have less number of processing nodes, does not require high-speed network. However, it requires partial decoding to be supported. So we have some comparative analysis between codecs, where we can favor JPEG for real-time performance. However, it requires the highest bandwidth. We can look at some alternatives, like deal directly with the vertical stripes, like individual images, or try to use the multi-view HVC or 3D HVC extension of the standards, which are better compressor, but very far from real time for the number of views we are dealing with. So this is the last slide of my presentation. So I'll take question and yes, please. So this is a video demonstrating the continuous parallax through the eye contact in a teleconferencing type of application. And yes, thank you for your attention.